Hello, everyone, and welcome to the 60th Cambridge Cheminformatics meeting. So we're going to start with the housekeeping slides and the presentations. So first of all, some introductions for those of you who arrived. Please sign in when you enter, because you've done this already, and don't forget to sign out when you leave the building. Hello? Okay, that's better. Yeah, then fire and safety. We don't expect any alarm test today. So if there's an alarm, it will be for real. So please go follow the signs and leave the building and go to the assembly point, which is outside the building near the chemistry of health. Next slide. So these meetings are intended to be to help people join the community and bring people together in the area of cheminformatics and related areas to forge network connections and share also interest in cheminformatics and new developments in the area. These meetings usually take place both in person and online, well, for those of you who have not registered to previous meetings. And the format is usually 3 talks from 3 speakers, 20-25 minutes for the talks, followed by 5 minutes of question and answers for the audience and also the audience here in person and online. So if you are online, please place your questions in the chat. We'll ask the questions at the end of the speaker's presentation. And for those of you attending here in the office, you will have the chance to ask the question directly to the speakers after the talk. This is the last meeting of 2025. Delighted to be here presenting this one. And the meeting will be recorded and uploaded to the internet for later on if you want to check the meeting afterwards. Well, as I said, questions. Any question, please place in the chat. After the last talk, we'll have a social event. We'll go to have a drink. Normally we go to the Phantom Arms, but for some issue, we'll move this time to the Alma pub. So please join if you are here to continue the discussions, hopefully in a friendly way, and to continue strengthening the networking and the relationships. So if you wish to present at the next meetings, please contact Andreas and let us know. And just before we start, just to mention that this was the 60th anniversary of the center, the CCDC. We normally held these meetings here in the office. We are very happy to do it. It's fantastic, and we hope to continue doing this in the next 60 years. Not sure if we all will be here then, but maybe the center will be, not us, but anyway, that's the aim. And now, with no more dilation, let me introduce you to the first speaker. So he's Christian Natajaya from Neopoly AI. Christian completed his degree in chemical engineering at the University of Texas, Austin, where he worked in a lab trying to find new polymer viscosifiers for enhanced oil recovery. Unsuccessfully, he decided to work in the chemical industry instead and implemented AI models into closed-loop process controls for distillation columns and reactors. Bored of this, he went back to pursue his master's in AI at UCLA and decided to tackle the molecular discovery problem that plagued him before. Christian is now trying to make a small contribution to pharmaceutical drug discovery by offering a new perspective on causal AI. So his talk is causal machine learning for property prediction and optimization. So Christian, the floor is yours. Welcome here.
Yeah, thanks for having me here. Yeah, so I'm pretty new face, pretty excited to meet you all and get to know you all a bit better. So just moved to London a bit over a year ago from UCLA out in Los Angeles, and now live in London and glad to be here in Cambridge. Nice place. So yeah, new face, new to drug discovery pharmaceuticals. And I just want to offer a new perspective today, just introduce this whole idea of causality and causal AI to our drug discovery workflow. So I'll start by saying that, property prediction has become quite a ubiquitous task from hit identification all the way to lead optimization. And, the properties range from solubility all the way to ME properties toxicity. And we've got an abundance, a plethora of your functions, FX that we can use right now to map these molecules to your properties. So you've got one school of thought, which is your classical ML models like random forests. And then you've got deep learning, and most commonly now your graph networks. And then recently you got agentic AI, where you got Bayesian optimization tools, LLMs to guide your experimentation and see what to synthesize and experiment next. And yet we still have one common problem that ties this whole thing, and it's the task of extrapolation. And so a common scenario is, okay, we have this training data, sparse or large or small, and it consists of, let's say, chemotypes A, B, and C. But now we want to make a prediction for a new chemotype D. And so this chemotype can be interstitial between all your chemical spaces or maybe outside, in the outside range. And so one thing that we could do is, okay, let's take our existing ML model and let's just make a naive prediction on this new chemotype. And I'll later show that this isn't exactly the best way to go. We see that the predictions don't do very well when we extract out of domain molecules. And one thing that's happening a lot right now is this thing called active learning, where, okay, we get some predictions with the existing model we have right now. Let's go synthesize some molecules, get some data from that, and let's retrain our model, and then let's make a second generation of predictions. But I guess a common question is how informative do we need this data to be? How big is it? How sparse does it need to be? So let's say our medical chemist does come back to us and say, okay, we have synthesized a new lead compound, in this case, ibuprofen. And let's say I want to predict the properties of its analog compounds. So with different decorators attached to your scaffold. So with active learning, you can, so with active learning, no worries. You can take this lead compound that you have, retrain your model. Not working. Okay, amazing. Yeah, you can take this lead compound, the new data you got, retrain your model, and make predictions for its analogs. But it's one data point really sufficient for you to help understand this new chemotype. How much is it going to help us? And so the question was, okay, what if our existing molecular representation was actually good enough? And so could we use this new data point that we have for ibuprofen as a statistical prior knowledge that we can use to advise future predictions for its analogs? Analogical reasoning, you might say. And so in a way, intuitively, could we bias existing relationships in our existing representation so that we don't need to retrain the model and we can still make predictions for its analogs? And essentially, how can we better leverage new data? So I wanted to take a step back and, yeah, like I said, causality. Just want to introduce really quickly this whole field of causal ML. So one of the frameworks that we can do to model causality is a structural causal model. And these impose structural relationships between your features in your representation. It's unidirectional, it's acyclic, and it does so, structural itself and the associative relationship. And these, each node would then be governed by a causal mechanism, which can be a linear regressor, can be a random forest classifier regressor, or it can be an MLP as well. So we've used this a lot in other sides of healthcare, so diagnostics, target identification, root cause analysis, fault analysis, you name it. But we haven't really seen it in the chemical sciences. And so with the structural causal model, there are a couple inferences that you can do. So Judea Pearl conceptualized your three causal inferences that you can do: association, intervention, and counterfactual. And so at the lowest rung, you've got association, where you're just trying to say, okay, you have temperature and you have solubility. Okay, how does temperature affect solubility? If you increase temperature, what happens to your solubility? And your second rung, you've got interventions, where you try to imagine a new scenario, right? So, okay, so if I have ibuprofen and I'm at 298 kelvins, what will the solubility be? And your counterfactual takes it one more up, where, okay, so my chemist found that ibuprofen has a solubility of X at 298 Kelvin. What will the solubility be at 313 Kelvin? And so in molecular terms, an intervention would just be essentially pretty similar to a forward inference we have with our ML models right now, where you take this new analog for ibuprofen and you just try to predict the property. So given the intervention on your molecular representation. But more interestingly, with a counterfactual inference, you can observe this lead compound, this ibuprofen molecule that this chemist came to you with, and you use that as a prior knowledge for your future predictions, right? So now not only are you predicting the target property, given the intervention of your analog, how you perturbed your ibuprofen molecule, but it's also given that you've observed this data point for ibuprofen. So just, so yeah, once again, conceptually, you can think of it where with this prior knowledge, you somewhat bias the view of your model into this certain region of your chemical space, and you're just making predictions around that chemical space because of the prior knowledge. And so it gives rise to more informed decisions. And so the goal is to apply all this, structural causal models and causal inferencing to property prediction. And one way that we can do that is with the use of learned representations. And so for small molecules, this would mean taking ChemProp, which takes in the smiles, gives you a learned representation, a learned embedding of a molecule. For proteins, enzymes, it could be something like ESM, the evolutionary scale model, where you can take all of your atom level embeddings and then aggregate them down to your sequence level. And then traditionally, what we'll do is feed these embeddings to a feed-forward network, which would then map it to your properties. But what we can do is we can take out this feed-forward network and replace it with a structural causal model. And so now each feature in your embedding is now structurally encoded with a structural causal model, with each node represented by a mechanism, which again can be a linear regressor or an MLP. And there are noises attached to each of these nodes. And these noises end up being really powerful because when you do observe a prior knowledge, you can abduct or extract noises specific to that chemical space, which will then advise future predictions. And so I mentioned intervention. That's one of the first causal inferences that we'll show. So basically, you take this new analog, and then you get the embedding out using ChemProp, and you pass it into your structural causal model, and we pass it through your do interventions. And in this case, we intervene on every node. And what happens when you intervene is you actually remove the causal influence of its parents. And so that's equivalent to just doing a do intervention on the parents of your target property, be it solubility or IC50. So we just plug in your features B prime and C prime into your nodes B and C and try to predict red, which is the target property here. And so we did this for a couple of data sets, namely IC50 predictions for kinase inhibitors and AQ solubility. And so we took it from the kinase knowledge base for RKIN inhibitors and ABL inhibitors. And we did the AQ solubility for your big SolDB and SolProp data sets. Did an 80-20 train test split and just show some results on your test set. So these are pretty small data sets. Your kinase data sets are about 500 data points, and your solubility was about 2,000 data points with 300 unique solutes. So this is a prediction that we have with ChemProp. It's not very good. It seems to just predict around the mean with some fluctuations above and below. And for solubility, it's pretty interesting. So each line there corresponds to one experiment where they actually tried different temperatures. And ideally, you want the lines to go up because the higher the temperature, the higher the solubility. So ChemProp doesn't capture that. It gets buried in the noise, and it doesn't take out this temperature dependence from the data itself, even with a sub-left loss. So with intervention based with causal ChemProp, we don't see big improvement. It's pretty marginal, right? Your RMSE doesn't go down by that much. Your Spearman doesn't go up by that much. Pearson doesn't go up by that much either. But what's interesting is with temperature, okay, with the solubility, we can manually explicitly add this edge between temperature and solubility. It starts to capture the dependence of temperature for solubility, where now increased temperature does lead to increased solubility. But the improvement isn't big, and that's not entirely surprising. After all, from everything I've said, we're still using the same representations that ChemProp gives us. So still the same representations, still the same features. The only difference is instead of using all your features, we're just taking 5-10 of those that directly precede your target property, in this case, IC50 or solubility, and then we just use those features. So you do see better generalization, more regularization, but besides that, it's still the same features, and we don't see much of an improvement. So we move on to counterfactual reasoning, right? Where now in this case we have these noise variables that we can carry over to our predictions. So we take a seed compound, and we observe this seed compound, and we observe the representation for this seed compound as target property. We take out those Z variables there, your noise variables, and then we carry over these biases for future predictions. So you have a new molecule, you embed it, and then you intervene on your intrinsic causal contributors, and you carry it down to your target property to go to the noise. To make this a truly extrapolative task, we did it on a whole different set of data that we know is completely out of domain. And so we took some pyridine RKIN inhibitors, some tyrosine ABL inhibitors, and a quinolynyl triazyl BIF inhibitor for the solubility. And we again tried to predict the IC50 and the solubility. And so we get some expected behavior from ChemProp where not only is it biased the wrong way, but also once again just seems to predict the mean value up and down. So not very informative. You don't get good separation of molecules, so the rank ordering isn't very clear. And these are the results when you do counterfactual reasoning with CAMPROP and with causal CAMPROP. And this is where you start seeing a bit of an improvement, right? So what happens is that when you see a seed pyridine molecule and you try to predict its analogs, you start understanding, okay, maybe we start getting a better mechanistic understanding of how different decorators affect your pyridine scaffold. Same thing with your tyrosine, same thing with your MIF inhibitor there. Yeah, so better rank ordering, better separation of molecules, and also better RMSE for all three tasks. Although, and so with improved predictions, this naturally lends to the question, okay, well, how does this help molecular design? And so for this project, we did something quite rudimentary. We used an evolutionary algorithm called EvoMol. So it starts with a bunch of seed molecules and perturbs these seed molecules iteratively. And at every iteration, you predict its properties. If it does better, that's your new seed molecule, which you will then perturb. And just do that until it converges to an optimal molecule. And so we did this for your MIF inhibitor and the solubility to optimize the solubility in water. And so you can use a variety of scoring functions for EvoMol. And in this case, we use CAMPROP as one. And we use counterfactual reasoning with causal CAMPROP as the other scoring function. And we notice when we use CAMPROP, it's pretty noisy. And you have really unstable trajectory for your evolution. So it cycles through a lot of different molecules at every iteration. And it converges pretty late at this molecule that doesn't seem very, very reasonable. Sure, it might be really soluble, but doesn't seem very reasonable. And so we swap it out with what I just talked about with causal CAMPROP and your counterfactual reasoning. And you see a big difference here. You start seeing a more stable trajectory where it cycles through less molecules through your evolution. And it comes out and it converges to this molecule that's surprisingly really similar to that proposed in the reference study. So with a double ether group, a carboxylic acid group, but instead of fluoride group, you now have an amine group. So this was pretty exciting for us. Well, of course, there's a catch, right? Not all counterfactual predictions are equally good. And so we noticed, so counterfactual reasoning uses your seed molecule, takes the biases and to advise future predictions. But what happens is that when your seed molecule starts deviating a lot from your target molecule, the accuracy of your counterfactual prediction starts going down. So this leads us to think, okay, what if we were to combine both trains of thought? What if we had a really good anchor, if we had a really good seed molecule, what if we did counterfactual reasoning? And if we didn't, what if we just made a naive intervention-based inference? And so we did this with PPAT enzymes. And we used your ESM model to embed it into a representation. And so reported by the paper here, and which I reproduce as well. So with ESM2, we get a Spearman correlation score of less than 0.2 for your PPAT homologs. It's not ideal. And so going back to the idea of anchor and similar enzymes, we used the basic local alignment search tool by the NIH. So just looking for pairwise sequence alignments, trying to see which enzymes in your train set are most similar to than your test set. And so for this case, what we simply did was, okay, for each enzyme in your test set, we found the most aligned enzyme in your train set, and we just took those activity score, the fitness landscape, and we just stubbed that in for your test set. And even that alone is better than ESM2, right? You get a Spearman correlation of 0.27. And so if you were to combine the both of them together, where, okay, if we had an enzyme that's really similar in your train set, we'll use that activity score. But if we didn't, then we'll use ESM. We get an even better score of 0.35 for your Spearman. And so if we were to substitute just using your PSA score with counterfactual reasoning with causal CAMPROP, where, okay, if we had a good sequence alignment, we'll observe that as a seed molecule and predict what's in your test set. We get an even improved Spearman correlation of 0.54. Yeah, and I believe this is approaching the aleatoric limits of your data with uncertainty and everything. So pretty exciting where you can combine both naive intervention and counterfactual prediction when you do have a strong anchor. So I just wanted to wrap it up and say that, this is not the next revolutionary model, and we're still using the same learned representations that CAMPROP and ESM gives us. So it's not a new model. We're still using the same representations, and this poses a problem to us, right? Along the way, trying to test reproducibility, we noticed that not all representations are learned equally. So we noticed that if I were to run it on my MacBook, if I were running it on Windows or Linux, we noticed that different devices actually do lead to different representations, even if we were to train the model with the same hyperparameters. We just don't see this impact with CAM-proper ESM because these are masked by a really deep feed-forward net that maps it to your properties. So we don't see these differences, but they exist. And what we noticed that even as minute the differences are, some representations are actually more causal than others, leading to more informed causal models that are able to extrapolate. And sometimes we don't get good causal models, and we can't extrapolate. So, case in point, some okay, good predictions, and then if we ran out of Windows, same parameters, same everything, we get a completely different result. So that's disappointing. And so we ask ourselves, what can we do to make this more robust? How can we make more robust representations that give us consistently good causal models that we can do consistently good inferences on? And the answer is causal representation learning. And so this is what we're still working on, where you make some forward inferences with your structural causal model. You have metrics like strength of causality or the presence of hidden confounders, or maybe just your prediction loss. And if we were able to backpropagate these back to your message passing network or back to USM, then maybe we can get better and more causal representations that we can build better structural causal models out of. So that's something that we're still working on. I'll be excited to share more in the future. So this was a collaborative effort with some folks out at MIT. So Lucas, part of Patrick Dole's group, and Jackson Burns is part of Professor Green's group at MIT. Yeah, done and open to any questions.
Thank you. This question it says causal machine learning. So they can hear also. So causal machine learning following Perl uses tags directed acyclic graphs to represent causal relationships, essentially just encoding conditional independence statements. Where do you get your DAGs from? Are you giving molecular graphs the interpretation as if they were causal graphs? And how do you validate how true?
Yeah. Good question. So it's all in the paper as well. So we use an open source framework to build a causal graph. We use this thing called DAGMA. So it's directed acyclic graphs with an M matrix acyclicity constraint. Long name. So this algorithm basically tries to maximize the likelihood of you regenerating your training distribution, and making sure, and with a constraint, making sure that that's right, that your graph is acyclic and is unidirectionally dependent. Are you giving the molecular graphs interpretation as if they were causal graphs? So I'm not. I'm just taking the molecular smiles and then I'm embedding them with either CAM-prop or ESM, you name it. And then I'm just taking these features of the representation and building a causal graph out of those. So I'm not treating the molecule itself as the causal graph. And how do you validate how true? I am not. So that's a really good point too. And so I do not have a ground truth model, and there's currently no way for me to say that the relationships between features are exactly causal and true. So this will be a future work to figure out some causal metrics, and one of which could be the presence of hidden confounders, and if there exists confounders, then maybe we haven't really found the true causal relationship.
One second.
Just going to ask, I mean, I'm looking at this from the medicinal chemistry perspective, where we like to make variations at various points and then check that they're additive. This seems to work quite well for that, but you might have to set up the test set, the training set very well. To get a good result.
Yeah.
Have you noticed great sensitivity to the training set?
Yeah. So I have not optimized it that way right now. That's a really good point. That's what we're doing with another collaboration now, actually. So right now we're just looking. We're using the same training set that CAM-prop uses and using the exact same data to train your structural causal model. So, but what we are planning to do is this idea called analogical reasoning, where you start fine-tuning what your training data looks like, right? So with analogical reasoning, you have, say, if you want to do scaffold hopping, if you want to choose your decorator, maybe you have done it with a different scaffold, maybe you've done it for a different decorator, right? So A to B, and now we have C, and we want to predict what D would be. And so we could curate our data so that we have a bunch of these A to B relationships, so that we now can do an analogical reasoning and say that, oh, because A leads to B, now we can see C leads to D. So yes, we can, so that is actually what we're working on, where we curate the training data so that we can more easily do analogical reasoning. But right now it is not fine-tuned.
Yeah, I mean, I think the value of that is that you're actually then training it to think like a medicinal chemist.
That's right. That's right.
So,
Yeah. But yes, no, that's a really good point. Fine-tuning the training data will be, I believe, a big improvement to the system.
So I had a question about the causal representation learning. So here you say you backprop into Chemprop and ESM2. Does it mean you are fine-tuning the nets directly, or are you using sort of adapter instead?
Yeah, so the reason why this is not mathematically possible is because your structural causal model is non-differentiable. So I haven't figured this out, but we do have an idea. So yeah, your structural causal model, your causal mechanisms are not differentiable, and so you cannot just simply backpropagate losses back to your MPNN. And so this gets a bit more philosophical, but we were thinking about something like abductive reasoning, right? Where you can create a hypothesis set of representations for a given chemical structure, and you can pass this hypothesis set of molecular representations to your structural causal model and see what target property it predicts. And eventually, you'll find one representation that does give you the right property that agrees with your experimental value. And so through abductive reasoning, then we can say that, okay, we should encode this chemical structure into this representation. So we do that for all the molecules in our training data, and then, could we train Chemprop again to encode molecules into this representation from a hypothesis set that we found out is the best. So we're thinking of reframing causal representation learning in that way, within the framework of abductive reasoning, instead of backpropagating through derivatives and everything.
I see.
Well, I think that in the interest of time, we're going to continue with the next speaker. Thank you very much.
Yeah,
So
thank you.
So our next speaker is Ruslan Kotlyarov, University of Cambridge. So his talk is DP5 without DFT, Uncertainty-Calibrated Graph Neural Net Accelerates Structure Confirmation via NMR. So Ruslan is an EPSRC postdoctoral pathway fellow at Yusuf Hamid Department of Chemistry, University of Cambridge. After working on stereoselective Suzuki reactions in Robert Phipps Research Group, he has completed his PhD at Syntec CDT in Professor Jonathan Goodman Research Group, where he researched selectivity of iridium-catalyzed carbon-hydrogen vorylation in collaboration with Exscientia. Ruslan now works on developing and using graph neural networks to make sense of NMR data and automate structural elucidation based on open source code and non-proprietary data. So please, let's give a welcome to Ruslan. Yes.
Right. Yes, so thank you for the kind introduction today. I will talk about how we can use uncertainty-calibrated neural networks to make sense of NMR spectra, and hopefully do it without running expensive quantum mechanical calculations. Why do we do this? Because technically in organic synthesis, we have two fundamental questions. One of them is making the molecule, which is as simple as getting from, say, point A to point B. And the second is making sense of what is it exactly we've made. I mean, we might have spent, years, if not, we might have spent years on end if it's sort of synthesis of some complicated targets. So we could ask ourselves, is this really what we wanted to make? For example, we might have, we might have a molecule like this, which is very similar to a snake in the sense that it is, it is flexible. If you ingest it, it will kill you, and you possibly can't get a nice crystalline structure because it is also bendy. And working out stereochemistry is really not straightforward. There are 4,000-ish potential diastereomers, and I mean, how do you even make sense of it? How do you even work out the stereochemistry? So there could be three ways. We could try and match it with database, but I guess in discovery setting, if you can find your compound in database, your intellectual property case is somewhat undermined. You could confirm it via synthesis, but unfortunately, we are all trained people who've undergone decades of education. So we are paid too much to confirm things via synthesis. So we have to resort to a secret third option, which is to simulate things computationally. And we did get to use DFT a lot, and we knew that the simulations weren't exactly perfect back then. So Alex has previously devised so-called DP5 method, where he ran the DFT calculation and he thought, okay, if this is a rigorous DFT-based method, it will systematically make errors in some environments. Say some environments will be under-predicted, some will be over-predicted, and based on what kind of environment we are in, it is possible to estimate the likely error, and we can ask ourselves: is the error we observed in the real spectra is the error we expected to see in this environment in first place? So the way it was done is we took a lovely piece of software package named QML. We featurized the atomic environments and computed similarities of our atomic environment to a reference data set, which we have curated from NMR-DB. We built a probability distribution based on these reference similarities, and then we integrated this for final score. Of course, if we want to, increase the throughput, if we want to make it more adaptable, or we run into some complications. For example, if we want to continue this method on the larger sets, the cost of prediction would increase with the data set size, and QML has proven itself to be quite hard to install via standard Python, automated Python package protocols, and DFT calculations are unfortunately quite slow. So we thought we could really use some, complete ground-up redesign, and as it always happens when we have simulations, but we do not have time, we build ourselves a neural network. And there is plenty of neural nets which could predict a single NMR shift, but there aren't too many which could generate a probability distribution. There is work by Jonas and Kuhn. There is an exciting preprint from Peyton Group, which has been published after we've started working on the project and after we wrote out most of it. But when the project was conceived, this was one of the few 3D graph neural nets which could do this. So in order to generate probability distribution, we initially thought we could just treat everything as a Gaussian distribution. We could get a mean, we could get a variance, and things would be so easy as to reduce the negative log likelihood, because that would mean that the experimental data would be quite likely under the model, and it has to be quite likely under the model. Unfortunately, we ran into a complication because the negative log likelihood could be easily gamed. You see two terms here. Both depend on uncertainty, so on variance. So you can systematically overestimate the variance. And I'm pretty sure in your times, you dealt with somebody who just, when you try and ask and you try and pin them down, they say, oh, I don't know. And you have to know being underconfident is as bad as being overconfident. So we had to think of different ways to generate a probability distribution we wanted. We resorted to we resorted to trying quantile regression. You might have seen all those regression, all the regression plots with, say, error bars. You see a line, you see some shaded area, which is 95% confidence interval, and you would be surprised to know that it works for multi-dimensional representations, such as one we get from the molecules as well. So, for example, if we have, this is X, if we if we try and predict, the values for several quantiles of the probability distribution, we will get the integrated. We'll get the cumulative distribution function. So in principle, we could recover the probability distribution from for that. And the way we set up the loss function is that we penalize it couldn't possibly overestimate its own uncertainty, because as you could see, we have to ensure that we both predict the accurate quantile and that it is not too far off from the target value. So this keeps the uncertainty much better calibrated than the previous approaches we tried. So we decided that this is quite a good way to estimate the uncertainty of prediction. You see at the top, we see what we get from the model. We get the empirical CDF, which we could easily imagine, which can be easily differentiate into PDF. So here, as you could see, we we set out integration limits as in, twice the difference between the predicted and observed value. And based on that, we essentially integrate the probability distribution and derive an atomic error score, which we then convert into a confidence score, and which we then make into the molecular score by just taking a geometric mean of them. So the first first sanity check we have to make sure that the model predictions, at least the predicted median is not too far off, because in addition to predicting its own uncertainty, still has to predict the spectra fairly well. And we did unfortunately observe some deterioration in mean absolute error. But then again, shouldn't possibly worry us, because previously we've been optimizing just for the single prediction, which should be the mean of the probability distribution. And here we optimize for, 99 data points. So what we might have lost in accuracy of predicting the median, we should potentially get back in terms of uncertainty estimation. So we would know more about the distribution despite the seemingly larger mean absolute error for the median. How do we so we do get the uncertainty calibrated neural network, but it is useless for its own sake. We aren't here in uncertainty calibration business. We are trying to make sense of the NMR spectra, and ideally we would be able to get the good data, and we'd able to generate some bad data, in the sense that we did not assign it correctly, and generating negative data might be a problem. Some studies resort to injecting some synthetic data via heuristics, via some machine learning models. We generate all the negative data from the data we already have, because if we have a database, we know which spectra the molecule has, and we know that this spectrum will not match any other molecules, so we can simply take them as the incorrect data. So if we had, n correct data points, we could get roughly n squared incorrect points if we use the common sense. So if we just make ourselves a little graph where we plot the DP5 score against mean absolute error, you could see that these are very well separated. So if we look both at the MAE and DP5, DP5 is in some aspects much better at telling apart the correct structures from wrong structures. And having an improvement over MAE is, of course, a sign of a great progress. But what we find is, while of course we could see that, okay, this is the DP5 score, this is the MAE, we aren't exactly recovering the total probability, and chances are we can't really recover the total probability, because we have to decide what is considered an incorrect assignment. So, for example, if we just simply lump everything with 6 carbon atoms together, if we don't really care about, say, maximum errors and whatnot, if we just throw everything in kitchen sink, we get quite a few negative examples, which will have, which might have low mean absolute errors, and we would have it look like this, and the resulting, say, total probability would be, say, 0.5 for this thing over here. But if we, say, discard most of the negative data and only look at the examples with matching molecular formula, we will get, of course, different numbers for the total probability score. So any attempts to get the absolute probability out of that have to be taken with a pinch of salt, because we need to know what we are comparing it against, what's in the pool, what are the other possible options. It's not that easy to, I guess, enumerate all plausible options. So it is quite hard to formulate like the big bird's eye view answer. Which is why it is best we go on and consider some particular some particular cases. So what we have found is that I mean, as our group is to some extent derived from people who actually did total synthesis, there have been many cases of people just getting a brand new exciting natural product, and they all ran into problems, in a sense that they ran all sorts of NMR spectra. They ran 1D, 2D, carbon, proton, maybe some NOE on the side. They could have run IR, they could have run UV, and despite the wealth of available data, they still got the structure wrong. So as a test, we thought, okay, if we take the original proposal and the revised proposal, which we know is correct because, say, somebody else has gone on and made the correct structure, or say they've looked at the database and they thought, okay, why are we inventing this molecule? Because there's no point inventing this molecule, because this one already exists and it fits fairly well. So we look at these natural products, and luckily, if we incorporate a quick ETKDG-based conformer search, we find that for almost all of these for all of these structures, the correct proposal has a higher score than the incorrect proposal does, which is an encouraging sign. And in principle, this should allow us, especially if the score is quite low, to just run a quick check and ask ourselves, is this correct, or do we need to rework our structure? So we were able to discriminate between the molecules with different carbon skeletons, and emboldened by that, we have decided to look at some intermediates of, again, total synthesis of various complexity. If you have dealt with some marine natural products and polyketides, we know they are flexible. We know that working out the stereochemistry is quite hard. So we thought this would be a nice, robust test. We had 42 molecules for which we had carbon NMR, and we have run the DP5 analysis of these. And when we tried doing this with just single force field conformer, we only got 12 cases out of 42, which is, well, not exciting. The chances are there's 20% chance we might have just gotten this result by randomly guessing. So clearly not looking at conformations is a bad idea, especially if we're dealing with some flexible molecules. Then again, we were pursuing some, throughput gains at cost of quite a few things. So we thought, can we just use, again, our DKIT's ETKDG conformer generation? And we were delighted to find out that when we do incorporate conformer generation, quick force field optimization and re-ranking, our accuracy shoots up to 25 cases out of 42. And if we just consider all the possible diastereomers which were present, getting this many correct is, well, there's a millionth of % chance that it is all has been done at random. And I guess if the chance of doing this at random is so low, means that it's a fairly robust way to do so. So having done that, we thought maybe we should incorporate, proton NMR, because as much as we like carbon NMRs, as much as they give us confidence in the structures, and they're usually nice, they usually look way nicer than protons do. We thought we could incorporate proton data and see if it could help us at all. And we could also try and verify the assignments, because suppose, we got a DP5 score of 0.5. Is this the best we could do? We don't know. And automating this would have been a good idea, really. So our Part 3 student Jasper has tried to train a very similar approach for Proton NMR, but unfortunately, as you could see, he took the very same 24 products, and you see there's a big overlap between the original products and the revised structures. And this is really not ideal when it comes to telling the molecules apart. Of course, it could be due to the fact that we used force field geometries as opposed to something more rigorous. Indeed, multiple studies suggest that for, I guess, accurate proton spectra, you have to, at the very least, do some machine learned potential, if not full DFT treatment. So this could be the reason. But again, we were chasing, prediction in under a minute. So this is the best we could get for protons. And if we just use these to, try and tell correct structures from wrong structures, we will be bitterly disappointed. And again, if we try and tell apart, if we try to tell the products apart, there is a great overlap. And we suspect that the only way we were able to tell these products apart by taking a geometric mean of carbon and proton DP5 was because they were well distinguished by carbon DP5 already. So protons did not really work as we hoped they would. And eventually we will get another master student who will fix it for us. Back in 2023, molecular optimization was all the rage. There was reinforcement learning this, reinforcement learning that. So what we thought we could also do is we could notice that DP5 is a score from 0 to 1, and quite a few molecular optimization frameworks do. If you give them any score from 0 to 1, they will try and generate the molecules with increasing scores. So it didn't work quite well to keep molecular formulae. The models were relentlessly cheating. They were proposing some unhinged stuff. They were, putting fluorine in where none has belonged. And out of all 24 examples, we only had one reassigned correctly by the mole-to-mole model trained on PubChem, and you'd think it knows all the chemical space, and it is able to explore everything around it. So this didn't work as well as expected. But then we tried, that implementation of Jensen's graph-based genetic algorithm, and as you could see, it has worked even worse based on molecular scores. So that would possibly lead us to two main takeaways of all that. Is that firstly, we possibly should, we have some data structures, we have some similarities, and potentially incorporating some approaches like variational Gaussian process regression would have been way better in terms of estimating uncertainty, because previously we might have gotten a well-calibrated neural net, but we had no way to check if the calibration of the neural net is aligned with similarities of atomic environments, and this would possibly allow us to just enforce similarity at the time of training and not bother. And now we could also try and work in the machine learning potentials such as AIMNet, because they appear to be given DFT accuracy geometries, and this may well help us getting much better proton data. And I guess the main takeaway about the optimization is that molecular, if we want to look at the molecular score, it is great when we're trying to make drugs. We want to make functional materials because we care about molecular properties there. But NMR spectroscopy is quite granular. The reason we use NMR spectroscopy, despite the fact that we need all this superconductors, we need liquid helium, this all we spend I guess millions of pounds to kit out a proper NMR lab. We still do it because it gives us atomic level insight. So what we are looking at now is we are trying to use the atomic confidence estimation. And having tried, the molecular optimization ways, we are looking into optimizing a molecular graph directly. Say we might, so suppose we feed we provide the structure, we estimate its shifts, and we try and optimize it into, say, its regioisomer. Because, for example, we might have gotten the wrong regioisomer, so we are looking into, optimizing the graph until we get the structure we want. And this could be a promising avenue for research we are already working on. Anyway, the code is available on GitHub. It should be fairly easy to install. It's much easier to install than it was 2 years ago. So this is utterly encouraging. I would like to thank Professor Jonathan Goodman, who unfortunately couldn't make it today. Jasper for, of course, taking taking lots of effort into getting the proton spectra to work, despite much worse data than that is available for carbons. Goodman Group, of course, for company. Syntax DDT for my PhD funding. Exscientia again for PhD funding, and their insightful comments when it came to revising our manuscripts. EPSRC for funding my current fellowship, Trinity College, again, for all the support they've given me all the years, and of course, my wife, family, and friends. Thank you.
Thank you very much, Ruslan. Do you have any question in the audience here?
Hi, thanks very much. So when we go to PubChem to look at natural products from various sub-databases, or including the ones that Chem will curate from the Journal of Natural Products, so how much salt are we supposed to take with them?
We are trying to incorporate this product into Atlas database developed by Roger Linnington and Simon Fraser University. So he could be better equipped to answer this question. But I guess I can't really answer. I can't really tell you how skeptically should we treat the Journal of Natural Products contribution. Although I heard it from Ian Fleming that we really should be skeptical, and I would trust Ian Fleming on that.
Any other question? I have one. You mentioned at the beginning that you were showing this compound with so many stereochemical centers. Is all the data you are using to train your model so well defined? So in which way lacking information of all the potential stereoisomers is having an impact in the way this method is able to predict or to match these structures?
Sorry. So I mean, discodermalite was there for the illustration. We weren't brave enough to try our model on discodermalite because I mean, it has what 12 or 13 stereocenters, so we didn't quite risk it. But I mean, it did matter for the people who were trying to make it, and I'm not sure we would have helped them then.
Yeah. What I meant was not with that molecule, but with other normal molecules, small ones with 1 or 2 stereocenters. How did you train all this? And if the data set you used to train your model was extensive enough, covering different stereocenters?
Well, I mean, it wasn't necessarily enriched with stereochemical data. We had to take the open source NMR database as there was. So stereochemistry is, getting stereochemistry right to this extent was a happy surprise, if anything.
Okay.
Although, of course, if there was, NMR ShipDB tier, curated database, we could have used that, of course, to adapt it to different portions of chemical space, definitely.
Okay, thank you. We have one comment over here saying that Ian Fleming once told me he can pick up a copy of a particular natural product journals and find a misassigned, misunderstood structure within a few minutes, given his level of practice.
Well, I mean, if for some reason we decide to wage a Butlerian jihad on NMR predicting, on all the NMR predicting stuff, we really need to pickle Ian Fleming's brain because he seems to be doing a better job on it.
Okay, thank you very much. So please, let's thank Ruslan for his talk and get ready for the next speaker. So we finally have with us Chris Southan. Dr. Christopher Southan is an expert in bioinformatics, cheminformatics, and drug discovery informatics with a career spanning over 4 decades. He has held roles,
Supposed to say that.
well, maybe, okay, just 2 decades. Nobody will know. Yeah, he has held roles and consulted for GSK, AstraZeneca, the EBI, the University of Edinburgh, Guide to Pharmacology, PubChem, and Medicine Discovery Catapult, contributing to proteomics, genomics, and patent mining. His work bridges experimental protein chemistry and with strategic data integration across biomedical domains. Dr. Southan has led teams, coordinated international surveys, and consulted for major pharmaceutical and informatics organizations via his company TW Informatics.
That's
Enough. It's a live.
you.
Come on.
Thank
Okay.
you.
Thank you very much.
Right.
The floor is
Okay.
yours. Oh, Arlo, you had
So,
Arlo.
thanks a lot. So is this okay? Can I have a pointer? Got a pointer? A laser pointer, or even a stick? You got a stick? No, never mind.
There.
Oh, that's all right. I'll point.
Well,
Well, there.
okay.
A mouse there. Ah,
yeah, the mouse.
all right. Okay, that's all right. Okay, good. Well, very nice to be here, and thanks to Andreas for the acceptance, and thanks to Kepa for being master of ceremonies, and yeah, splendid to be on the 60th anniversary. So, yeah, I have an affiliation with the University of Edinburgh from the time I worked for the Guide to Pharmacology database. So, but I was working remotely, so I live in Sweden and do some consulting from there. So I'm going to tell you a little bit about deuteration and look at the atorvastatin example in PubChem. A little bit about this the gold rush that happened about 10 years ago, and some PubChem totals. An interesting example for max deuteration from codeine, and the effect on Unichem of very few approvals. I introduced some conclusions and some implications and a few links from me. Okay, so this is all fairly old stuff, well established back in the 60s and 70s nearly. Okay, the CD bond is stronger than the CH bond, harder to break, slow metabolism, altered metabolite profiles. So all these the good properties on a good day for the right compound. Okay, and selective deuteration, control over metabolic pathways, and because the structural change is so small, usually the in vitro affinities are very similar. Yeah, but they can be slightly different. So, and you've got a better therapeutic window and reduced side effects, less frequent dosing. And I'll touch on this issue at the bottom, which is patent extension of existing drugs. Now, if you spend a bit of time in PubChem, years ago I was looking at the namespace, the different names for the salts and the isomers and stuff for some known drugs, and I looked at atorvastatin. And if you go to PubChem and click on same connectivity, so this is essentially the core structure, roughly equivalent to the inner Inchy key. Okay, you find surprisingly enough 56 same connectivity relationships of atorvastatin. Some of these are that inner key is in fact isomeric and isotopically agnostic. Okay, so and if you look at these, you've got these pretty heavy deuteration forms right at the top if you rank by molecular weight. So where on earth did all this come from? So here's the here's a pièce de résistance, a D34 atorvastatin, right? I propose it's synthetically implausible. It must be very difficult to make if you wanted to put replace all those hydrogens. And it turned out, it actually turned out that so this is a CID from single submission from Thomson Pharma, who were curating up to about 2016, submitting to PubChem. That's the substance ID, and that came in at back in 2011. It turns out you can find a patent which this was almost certainly the same patent that this was extracted from, manually by Thomson Pharma. Okay, back in the day. So there it is, and this is from deuterium enriched atorvastatin. Hey, don't you know? and this guy, Sarnik, was from Protea, which I'll mention again because he's got hundreds of filings. So this is kind of this is an aside, which is interesting on the automated or semi-automated extraction of structures from patterns. Okay, now if you throw that image into Decima, which is my favorite image to structure program, it's actually most of the time it's very, very good, but it recognizes the deuterium in the smiles and it'll render in PubChem if you put it in, but it actually doesn't actually render them in the web application. So going back, this is the virtual patenting gold rush, around about starting in 2006 to go through to 2011. So Nature already picked it up in 2009. Big interest in heavy drugs. This was the headline from in the pipeline back in 2009, where he says that the patent office is beginning to say, okay, that's actually controvertible. And there was an interesting comment, a pithy comment under the post from Derek Lowe, saying most of these patents, these deuterated compounds, stem from just 3 companies: Allspex, Concert, and Protea. And particularly Protea, they had a blunderbuss, a massive 237 US filings. Okay, and these don't show reduction to practice. Okay, they haven't got supporting data on those. It's not, they may not have actually made the stuff. Okay, so then Concert has quite a lot of 39. Allspex had quite a lot. So yeah, so there you go. That's what was happening then, and that was the gold rush. Okay. This is a nice, you can go into PubChem and find these, okay, and actually PubChem indexes patent titles, which is very good, and will index applicants. So you can go in and find actually this Anthony Tonic. He's in my LinkedIn profile, but I haven't actually challenged him about what he was doing back then. But lo and behold, he's been fairly productive. Okay, 232 patents. But I don't think he's productive in making the stuff. Okay, so there they are. Now, if you go into PubChem now today, and you do a smart search for deuterium, you come up with just over 500,000. Okay, so that's actually surprising. One of the unusual approved drugs has actually come up to the top there. We look at these, look at what these are picking up. So you can push it across the entree and you get the full PubMed. On the right, you get the default statistical breakdowns from the PubChem defaults. Top are my own filters that I put into my NCBI. So there's a few things. I've got CNER patent sources, so about 85% of these are from automated patent extraction sources. The rest of them are the old Thomson Farmer stuff that came through before 2016. So there's a surprise. There's a few curated by the Guide to Pharmacology as lead compounds. So a few of those have come through, and there's some activities indexed from Kemble and from BindingDB. But overall, the number of assay results out of these 500,000 is really absolutely tiny. Okay, so that's the feature of all these. Now, I started looking at. Actually surprised to see this because I only done it fairly recently. So if you plot the deuterated 500,000 versus time. You see, this is the Thomson Farmer blip. Okay, so they're coming in there, and this is where some of the automated extraction, I think, was Shaw Kemmler the earliest, followed by PatentScope, and then followed by Google Patents. but you got this big surge here just a few years ago, which may be suspicious. I wonder what on earth is going on. So if I now split this by submitter, you see the lion's share is from Google Patents. Bless them. Okay. Now the problem there is, of course, Google Patents. If the deuterated compounds in Google Patents in PubChem are 49% are mixtures. Okay, and this is a real problem with Google Patents, that they'll take out the mixtures. So they'll extract a whole page and submit it in as one substance ID. Okay, so PubChem will split them, of course, but it makes a mess. So you see, more reasonably, Shawchem will down at 0.1% mixtures, patent scope very low as well. This is the Thompson Pharma that stopped. IBM stopped in 2017. So the automated pipelines have been pulling out some of the deuterated compounds. So this was I think it's the all-time record here for, if you go to codeine and put the same connectivity in, you have no less than 522 deuterations. So that's quite heavy going. So 515 of these are from automated patent extraction. I didn't check what source unique is, but of course none of these have any activity so Kemble didn't pull it out, Binding DP and Guide Pharmacology didn't pull them out either. So I don't think there's any assay results for this set. That's why that markup is empty. So where the hell did these come from? So it looks as though the culprit, or the smoking gun, is in fact a patent from Auspex in 2008. There it is, preparation utility of opioid analytics. PubChem's pulled out about 1,500. The automated PubChem submitters have pulled out about 1,500 compounds. But here I think there's pages and pages of these virtual deuterations, and that's what's come through for the 520. So I think that's the most I managed to find. And oddly enough, this was actually granted. It had a B2 in 2011. So make of that what you will. And there's no obvious experimental data in that patent. Now, of course, what PubChem has to grapple with, because the Unichem chemistry system at the EBI subsumes PubChem anyways. Okay, so it gets what PubChem throws it in the negative sense. So here, this is a connectivity search. So that's the inner inchy key for codeine in Unichem. You get no less than 829. So I think this is a mixture between the isomers and the isomers and the deuteration. So it's a bit of a mess. Okay, so they indicate that on their entries. So why did they bother back then? Well, it's fairly simple. What they did is they just were picking off the best-selling drugs back then. I compiled this in about 2019. So the rank is the sales of the small molecules. Some of them are combinations here, but you can see same connectivity in almost all the cases. Most of the same connectivity multiplexing is from deuteration. The one exception is the fluticasone, whatever it is, has obviously a lot of stereo, more stereo than deuteration. But for the rest of them, it's made deuteration. So yeah, and these were US patents claiming these roughly from 2006 to 2011. So I plotted this also from PubChem. I think did this at about 2019, and it has a strange implication. Basically, if you intersect the structures from Auspex, Concert, and Protea, they're more or less non-overlapping. Now, my interpretation of this is that they must have syndicated back then to split up the to split up the best-selling drugs amongst themselves, because they say they avoid the prior art clashes and the infringement overlaps. So I suppose, you know, we all know it's in terms of all's fair in love, war, and pharmaceutical patenting. So I'm not even sure whether it's illegal in patent law, but it looks as though that's what they were doing. So there it was. That's it was kind of a Deuterogate thing, if you like. So finishing off a bit, okay, so after all this activity and say 500,000 deuterates in PubChem, after 50 years, this is an extensive review back from 1975. Okay, so it was kind of cat was well out of the bag there. You got these 3 FDA approvals. This is the deuterobenzene. This is from Auspex, taken over by Teva. This is from Concert, taken over by Vertex. But this does look like an independent BMS effort. I've looked at the patent, and it looks as though they actually have some real data there. So there are some successes. Very slow. Okay, so these early blunderbuss filings by those 3 were curated by Thomson Pharma manually and sent through to PubChem. So this resulted in about 25,000 virtual deuterations of these best-selling drugs coming into PubChem. Kind of unintended consequences, right? So, but close to 0 reduction to practice of real supporting data, or that they were ever made. Okay, so these 3 and all 3 major current automated patent extractions, Shaw, Campbell, PatentScope, and Google Patents, have been submitting deuterated structures to PubChem. And the Google Patents submission of mixtures is really problematic. So that's giving us a deuteration inflation, because it's looking at whole pages of the stuff which mentions some of the reagents in. So what the IP situation is a bit unclear. It always was this issue of obviousness, but the USPTO passed some of them. So those early patents are nearly expiring. So is this a tragedy of the commons, in as much as were there instances where some of those approved drugs would have had more effective deuterated derivatives if the data had been there for a strong filing? So the pharma companies now include deuteration in their exemplifications. Quite what the ramifications of that are, that is unclear. And as I said, there are very few deuterated drug approvals or late stage development compounds. So for us as cheminformaticians, does any of this really matter? Well, maybe in the grand scheme of things, perhaps not. But remember, the problem of submission databases is that those virtual deuterations, they will be there forever. Okay, so now, admittedly, Thomson Pharma is now marked as a legacy resource in PubChem, so it's kind of flagged, but that isn't very obvious for the individual entries. And Thomson Pharma was an excellent database, in fact, for curation from papers and patents. So you get this problematic, the multiplexing of CIDs in PubChem according to that same connectivity parameters. So, and also the same, what PubChem gets, Unichem gets, and ChemSpider and SciFinder as well. Okay, so these pharmaceutical crown jewels of their old marketed drugs are badly hit in terms of the multiplexing. All right, and less experienced PubChem users, they can be, or cheminformaticians can be confused in the search space of what these are there. So your neighborhood search results get a bit messed up. And when I worked at AstraZeneca in 2010, 9-10 on Chemistry Connect, they will also they'll be kludging up internal compound collections. Yeah, they're there, so difficult to get rid of them. And actually, PubChem we don't really want prophetic and virtual structures in PubChem. We'd rather have things that were just actually really made and done some experiments with. That's it. Thank you. That's it. It's a few links from me. I will put these slides up on Zenodo when I get back. So, questions, please. Thank you very much.
Thank you very much, Chris. Do we have any question in the audience? No? Okay, just a curiosity. Somehow, how all this can impact the market of these drugs if someone decides that deuterated drugs are different drugs?
Yeah, I'm not an IP expert, right?
Yeah.
I could see the consequences of IP
be
when I was
massive.
mining patents. So early enough, the controversy of obviousness was raised very early on, but some of the US appears to have granted a fair number of these, but those early ones are nearly expired. So I've no idea what the current IP situation will be, because it still stands that the deuteration could give significant improvements to the marketed compounds. Yeah, but very few appear to have come through. Whether that's an IP issue, I don't know. Maybe AI will help us determine exactly which positions to deuterate for the effects that we want. That would be nice, wouldn't it? Yeah.
Well, could be, yeah. Or not, or
Yeah.
be a mess. Who knows? Any idea? Any more inputs? So what would happen, for example, if someone decides that just a single hydrogen is deuterated, not the rest of the molecule? Could they still patent that molecule? I imagine no, because it won't be, the change wouldn't be so different as having the entire molecule.
If you show by data
Yeah.
that it's really improving,
Yeah.
and not non-obviously a non-obvious improvement in the properties, wherever you put the deuteration or
Yeah.
how many deuterations you put in, you should, I think, have an IP position.
Yeah, but that would be tricky. Let's say, for example, that someone get that idea through, and then they patent one molecule with one hydrogen deuterated that enables these differences in activity. Could one of these companies potentially block the initial development of this drug?
That's what
Say you can assure that your compound does not contain any molecule with one deuter.
Well, I really don't know, but say it would. So they effectively then, back then, they kind of blanketed prior art. They put deuterations, they put deuterons everywhere. Okay.
Yeah.
But I still say, I think if you, whatever you did with deuteration experimentally and supported and proved it was you'd significantly improved the properties of that drug, I think you'd have an IP position. Yeah. But that's.
Yeah, my question was more in the direction of naturally occurring. You may have one molecule every, I don't know how many thousand.
Oh, that's a bit beyond mine.
Yeah.
I don't know, yeah.
So naturally, you could say this molecule is mine. It's not from the.
Yeah.
Then they may force the original drug company to get an agreement.
They have to ask a lawyer. Yeah.
Yeah. That's the thing. We are entering to the lawyers area. Okay. So, yeah.
You've highlighted deuteration here. Is it your sense that, I mean, are there areas where a chemical modification has been?
Well, it's interesting. I immediately thought on that smart, so I've actually put tritium through. Okay. Right. And that's quite high for 400. But we know tritium is a widely used reagent molecules, more so I think than deuterium. But they also had very low activities, very low activities in PubChem bioassay. So I suspect they're pretty low in experimental confirmation. I was going to do one day. I'll do C12 as well and see what's happening.
But I mean, it same could apply to certain chemical groups. I'm guessing phosphonates replacing sulfonates, that kind of thing.
Yeah. You go on and on with those types of queries, but yeah, I'll see.
Okay, thank you very much. So if there are no more questions, let me thank you, Chris, again, and get ready for closing up these
Yeah.
meetings and continue with the social meeting after this. Thank you very much, Chris.